This lecture will be on global warming, and the emphasis will be to show the data which substantiates the fact that climate and global warming is occurring. And we're going to concentrate on the facts and the data and not on the politics, because I know that global warming can become a political issue. So what I want to do is I want to explain why 97% of the scientists working in America on this believe that global warming is not only taking place, but that it's something to be very concerned about, and then you can make the decision on your own as to what you think we should do about this, in what actions we should take. First of all, I'm showing you this graph. It's a temperature of planet Earth in the past for 500 million years. The scale at the bottom is a log scale, so make sure that you recognize that. And then we've got a temperature which is based on an average over, well, it's given there in the parentheses. And note that there hasn't been a tremendous amount of climate variation over the last 10,000 years or so, a little bit longer. And then things go crazy in the past. There's a lot of different ways to calculate these different temperatures. I won't go into the details, but suffice it to say the temperature has varied in the past a great deal. So you may ask, why would we ever worry about then temperature going up today? Well, we know, first of all, that a lot of the temperature in the past was due to great upheavals. And so anything that might disturb our climate should be of concern to all of us. And take a look at the stability we've had in temperature over the last 10,000 years, and then take a look at what they're predicting there on the far right for temperatures by 2100. You can see that it's well above what we were seeing 200,000 years ago or so. Except for a few spikes, we might even be able to go back 3 million years without seeing the temperatures that we've seen over that period of time. So we are headed potentially in 2100, unless we take some action now, we're headed towards the temperature values that you see marked there by 2100 by the end of this century. I'm not hysterical. I'm just trying to point out the facts there. These climate models we'll take a look at a little bit later on, and you'll get to see how they function. All right, now on this graph, I've taken the temperatures, or the graph shows us temperatures from about 1880, their annual mean temperatures, the black dots, and then there's a 5-year running average. And it shows us the temperature anomalies. The average is between 1951 and 1980. You can see it's rather stable during that period of time. So they divide by that average so that you can get this temperature anomaly that you see in degrees centigrade there on the y-axis. One of the things to note is that in the 1880s through, say, 1930, there was pretty stable temperature in the world. And then it started increasing towards the late 1930s, increased through the mid-1940s, and then started to drop. And it got stable once again, although at a higher level. It got stable again through the 1950s and into the 1960s, even the 1970s. And then in 1980, we started seeing distinct temperature increases going up all the way through to today. And it turns out that, and as you can see from the diagram, 2015 was the hottest year on record. So and I'm going to keep referring back to this, there's been a lot of anti-global warming people out there, and it's we were finding been funded by the oil industries to have this disinformation about what scientists are saying. I can give you books about this if you want to contact me, if you want to read about it. There are 45 district attorneys in the United States right now looking into whether they want to bring charges against Exxon for this disinformation, purposely misleading the public on global climate change. This is a serious issue. I want to take a look at the hard facts. This is an example of some of the hard facts. We have seen a 0.85 rise in temperature in degrees centigrade, that's a lot more in Fahrenheit, since about late 1970s, as you can see there. And it doesn't seem to be slowing down at all, especially here in 2015 and 2014. And it looks to be another hot year here in 2016. All right, so let's switch now and take a look at global temperatures. This is the temperature trends for degrees centigrade per decade over a period of 1950 to 2014. And as you can see, the cooler regions there's only really one cooler region during this period of time, and that's down in Antarctica. There have been some places that are staying about the same, for example, eastern United States and just off the coast. But look where it's tending to warm the most. It's tending to warm the most in the Arctic and in the continents, the northern continents like Asia and Europe and North America. And of course that's where our tundra is, that's where the Arctic ice is. That tundra, which is frozen earth frozen soil down to a certain level, is melting, and when that melts, it also releases carbon dioxide. So we're putting more carbon dioxide in because we're melting the tundra. We're melting the ice at the Arctic. You cannot take boats across the Arctic Sea during the warmer months, as we'll see in just a minute here. Well, this is 2015. Temperatures worldwide. This is taken from 6,300 independent weather stations around the world, and please note that it's actually quite similar to the one you saw before. We have Antarctica, which tends to be cooling in 2015. We have this little kind of hole there around Greenland, or just in the southern part of Greenland, and everything else is getting extremely hot in 2015. Look at Asia and Europe, look at northern North America and Canada, that region. We are getting, we're seeing very high temperatures in 2015. Now, I have to point out, in fairness, 2015 is a El Nino year, and we would anticipate some of this warming due to El Nino. But it does not look that much different in 2015 than it did in 2014. That's the concern. Let's go look at some data. This is data on carbon dioxide. Carbon dioxide is considered a greenhouse gas. So let me explain just briefly what I mean by a greenhouse gas, so there's no misunderstanding. These are gases that go in the atmosphere, and it operates like a greenhouse. Light comes into a greenhouse through the glass, but when it reflects back out, the temperature can't get out, and so everything is warm in a greenhouse. And that's the idea with greenhouse gases. When we increase the atmosphere in these gases, they tend to trap the heat, and the heat can't escape. And we'll see how different wavelengths of light are prevented from escaping in some graphs in a minute. Right here, this is carbon dioxide in parts per million. That is, for every part that's measured, there are 1 million particles. So it's conceptually fairly easy. From about 1950, well, not from about, from 1958 to the present. And you can see the squiggly lines there. That's because we do have an annual variation. That black line is measuring the average, but the red line is measuring actually each measurement during the year. And they took a series of measurements. And we get this variation because in the northern latitudes, the vegetation, there's more land in the northern latitudes, and vegetation during the summer tends to absorb a lot of carbon dioxide. So it reduces carbon dioxide worldwide, but during the winters it increases. So that's why you have those very consistent squiggles in the line. But I hope you can see that in general we are increasing in carbon dioxide. I don't think anybody would argue that. When they started making these measurements in 1958, they had already increased in carbon dioxide. We can go back and look at that data. We were below 300 parts per million in the last century, and now we've finally gone over 400 parts per million. Now I know that doesn't seem like a lot, but we'll see the power of carbon dioxide and its ability to cause global warming. And they've been predicting this. Scientists started to recognize this in the 1950s and 1960s, that carbon dioxide and other gases would be a problem in warming the planet potentially, and those predictions are beginning to come true. The data is now far more shocking. Let's take a look at this diagram. This is a graph of carbon dioxide again, but over a much greater period of time. Now we can get carbon dioxide concentrations in the past by taking cores from the great ice sheets of the world, either in Greenland or in Antarctica. This data, I believe, comes from Vostok, which is a drilling site the Russians are running. And they took ice cores out of that, and trapped within those ice cores are little bubbles. When the snow falls and it turns into ice and gets into the glacier, every year little bubbles of air get trapped, and we can actually go into those ice cores and measure the carbon dioxide concentrations of the ice cores. So we have this beautiful record of carbon dioxide concentrations in our atmosphere over the last 650,000 years, as you can see in this graph. Now, a couple important things to note. We know these carbon dioxide concentrations are real because they track temperature variations, which we also can measure, and they also track the Milankovitch cycles. So we get rises in carbon dioxide, as one would expect, because the Milankovitch cycle is warming the Earth. So it tracks very nicely with Milankovitch cycle and temperature. Well, the startling thing is that we have not had, in the last 650,000 years, actually going back farther, we have not had carbon dioxide go over 300 parts per million, as you can see on this diagram. But in the 1950s, we saw carbon dioxide go over 300 parts per million, and look at it today. It's astronomically high. We just went over 400 parts per million in 2015, and it's anticipated to keep going up. So we should recognize this and try to understand what it's going to do to our planet, and that's actually what this talk is all about. Well, here's a graph of our greenhouse gases, and as you can see, the major gas is nitrogen in our atmosphere, and then oxygen, and we got a little bit of argon, and then the rest are minor concentrations of various gases. I've listed the major greenhouse gases on the right of this diagram, and they're primarily water, carbon dioxide, methane, ozone, as you can see, and nitrogen, and then also CFCs. Now, CFCs has become less important because the CFCs were having a tremendous impact on the ozone, so we actually banned the use of CFCs in the world. All the countries signed on to that ban, and our CFCs are dropping. So CFCs were a major source of greenhouse warming, but because of the cease in use of CFCs, it was fought hard by the industries, by the way, but because of that, we've not only starting to get our ozone layer back, but we're not having a big impact from CFCs anymore on the global warming. But the big impact, I would say, is carbon dioxide, and also we should consider methane and water as big and important too. I'll show you a graph later on of the impact of these various gases on the diagram, or I should say on global warming. Well, this diagram is perhaps one of the most important diagrams I'm going to talk about, and I hope that it'll clear up why we have global warming and why we should be concerned about it. First of all, I have on the x-axis plotted the wavelength, and I'm going to be concerned about the top part of the graph at first, and I want to look at that red line. That red line is actually what we call a Planck black body radiation. All it is the radiation coming from the sun that reaches the top of the atmosphere. And you could recreate that by heating up a black box, and then the amount of energy coming off that black box would give us a similar curve as to the sun if we heated it up to around 5,000 degrees, 5,778 to be precise. So you can see then what light is hitting the Earth's atmosphere, and if you look over on the blue, notice that it's completely separate, the blue curve, and that's the amount of radiation coming off of the Earth. So it's very different wavelengths than the wavelengths that hit us from the sun. Well, a couple of things. The blue curve is actually the average between the surface, which is the black curve, and the black curve is of the upper atmosphere that's radiated out. That's at 210 degrees, and the purple curve is at the surface, which is 310 degrees. So the blue curve is kind of an average of the amount of radiation. And so we'll see then in just a minute talk about how much of that radiation is actually escaping and how much is trapped. Let's go back over now to the red. The area that's filled in the red, that's the area that is actually reaching the surface of the Earth. The rest of it is absorbed by the atmosphere. If you look right below that diagram, you'll see UV, visible, and infrared. Most of the UV radiation that's coming into the planet is absorbed by the atmosphere, and in particular by ozone. Go down to the bottom and look at oxygen and ozone down there, and you can see that it's absorbing most of the wavelengths of UV. That's good news because UV is very dangerous and deadly to us, and that's one of the reasons why we were trying to protect our ozone. We saw cancer rates go up drastically when we started destroying our ozone because more UV light was getting in. So skin cancers now, we won't have the kind of skin cancers that we were seeing because we're now protecting our ozone much better. Well, you can see small little sort of valleys in that red area, and that's due to a water absorption. So water in the atmosphere is absorbing in specific wavelengths, and that's why you're getting some of that red curve being absorbed as the light comes through our atmosphere. What's remarkable is in the blue, by the way, it's no chance that we see in the visible part of the spectrum, look, all the light coming in, or a great deal of the light coming in to Earth is within the visible spectrum. So this is pretty clearly shows that we have a region where life could evolve to see in that spectrum. And who knows, we might have developed an ability to see in some other wavelength if that was the way the light was coming in. Well, the blue curve now, or the blue area below the blue curve, that's the amount of light that is transmitted or sent back out into space, reflected back out into space, and doesn't affect us here. But look, below the blue curve, much of it is being absorbed by the atmosphere as it's trying to radiate out. And that's what we're talking about when we talk about the greenhouse effect. It's in the near and far infrared where absorption is occurring. And if you'll go down and you look at water vapor and carbon dioxide, you can see that most of that those wavelengths are absorbed by primarily water and primarily carbon dioxide. Methane and ozone and nitrous oxide, they all have a little bit of absorption, but carbon dioxide and water are the two major ones, and carbon dioxide is what we're increasing so rapidly in our atmosphere, and that's why we have to be very concerned about it. Now let me show you a blow-up here of the absorption due to water and carbon dioxide. We're looking at the wavelengths we saw in the last diagram. We're just blowing it up a little bit. Look at where carbon dioxide is there in the purple and water in the blue, and this is why, as we increase carbon dioxide in particular, and water also in the atmosphere, we see energy being trapped. It can't get back outside the Earth for obvious reasons. So there is reason to be concerned. The data is telling us that. All right, this diagram I think is important to understand the process. We can actually measure in watts per meter squared what's being absorbed and what's coming in. So let's take a look at that. Let's start with 342 watts per meter squared that we have coming in from the sun. 77% of that is reflected off of the clouds. I should say not 77%, but 77 watts per meter squared is being reflected back out into space. You get another 30 down there reflected by the Earth's surface. And then you also get 67 watts per meter squared that's absorbed by the atmosphere and doesn't hit Earth. By the time you get the light, though, hitting the surface, you have 168 watts per meter squared that hits the surface of the Earth. If we can look at how much is also sent off into space, the radiation can also occur in what's called thermals. So we have 24 watts per meter squared coming off, and then we also have latent heat, which is through evapotranspiration, and that's 78 coming off that way. Well, reflection off of the surface of the Earth is 390 watts per meter squared, and then 40 of that goes directly out through the atmosphere and out into space. Another 165 is radiated out, emitted by the atmosphere, and ends up being a total with the 30 that you see there emitted by clouds, a total of 235 watts per meter squared escapes to Earth, outside of Earth. The rest, this huge amount of 324, is back radiation. That is, it's absorbed and kept inside the Earth and comes back down and hits Earth and is absorbed in our atmosphere and on the surface of the Earth. So look at what hits the Earth from the sun directly. It's 168, and look what hits it as back radiation, 324. We've got an immense amount due to the greenhouse